Kind of weird question for you. Have you seen my car keys? I know. With today's technology, it's kind of crazy. We still have to look for lost car keys, or anything else for that matter. My full time earbuds should say, the remote control is under the second sofa cushion from the left, along with 37 cents in change and several popcorn kernels. Actually, for that matter, why do we even need remote controls or car keys anymore? My car should just know when I'm walking toward it, open the door, adjust my seat, cue up my favorite playlist, set the temperature where I like it, and say, "Welcome to your car, Amelia. Where are we going today?" Hi, I'm Amelia Dalton, host of Chalk Talk, and guess what? A lot of big technical barriers to providing these kinds of features are overcome by ultra wideband technology, or UWB. And before my intelligent car whisks me away, let's talk to an expert about it. I've got Mikhail Viel from Qorvo here to give us the lowdown on accurate, low-power indoor location tracking and a host of other cool applications for UWB technology. All right, let's go. And before we get started, don't forget to click that link. There you can find even more information about Qorvo's ultra-wideband technology solutions. Hi, Mikhail. Thank you so much for joining me.
Hey, good morning, Amelia. Really happy to join you today.
All right, so we're talking about the newest and coolest in location technologies. But in terms of location information, we have come a long way in a relatively short amount of time, right, Mikhail?
Oh, yes, definitely. Within the last 20 years, there's been a lot of innovation when it comes to location technology. And location technology has had a major impact on people's life and also gave birth to new services and businesses. For most of us, it all started in the late 90s, early 2000s, when GPS began to be used by civilians for navigational purposes. You remember like finding an ATM, finding the nearest gas station? Prior to that, we all had to use those old-fashioned way paper maps, asking people for directions. Maybe it was better to talk to people, but you had to do trial and error to navigate ourselves around the world. The new level of convenience that was brought by GPS really changed our lives as individuals. But if you think for a minute about the benefits for businesses, it goes way beyond convenience. It is a matter of efficiency or even a matter of building sustainable business models. Just think about how difficult it would have been for companies like Amazon to efficiently navigate deliveries without having GPS technology. I don't think that would have been possible. Then 10 years later, we saw the start of indoor navigation. Think about like Google Maps for malls, airports, and other large buildings. Location data value increased even more thanks to new indoor location-based services like finding shops. For the individuals, it makes navigating large indoor spaces much more convenient and efficient. But again, if you think for businesses, a good way finding and location data leads to sales growth and more granular consumer data. Fast forward to today, we're now seeing the rise of micro-location-based systems. Like the first GPS systems were a bit frustrating. They were not super accurate, they were a bit slow. How many exits have you missed with your first GPS? It's a bit the same with the first generation of indoor location services. They have not fully delivered on individuals' and businesses' expectations. Indeed, what people and businesses want is to be able to locate and find pretty much anything in real time, whatever the size. From your remote control, which always magically ends up lost in your living room, to the exact location of your favorite bread as you navigate an unknown store, that works with wine as well, to this infusion pump, which was supposed to be on shelf A, room 12 on the third floor, and that you urgently need. But the current systems cannot offer enough accuracy, reliability, and real-time capability because the underlying technology they are using were not designed for accurate location.
So, Mikhail, when it comes to defining where, we're finding out a lot more than just an accurate location. Is that true?
Oh, yeah, that's entirely correct. I just gave a couple of examples to start with around finding stuff, because that's the most obvious benefit of location technology, finding stuff or finding your way. But if we step back just for a minute, we're all familiar with the Internet of Things and the benefits of being able to collect data from billions of things. But what if, in addition to the what, the data we're getting from sensors, and the when, that's what we get from the system clocks of those devices, we could also answer the where. Adding this third dimension is like adding a sixth sense that would give us much more insights and allow us to develop context-aware products and services. Knowing where people and objects are in real time is key to enable contextual decision making, whether it's to adjust your stereo system automatically as you move from one room to the other, control objects by simply pointing at them, or avoid having your robot vacuum cleaner turn on as you take an unplanned nap in the couch. Knowing where assets are located in real time, where they have been, who operates them, also helps improve their utilization rate in factories, reduce maintenance costs. Having a real-time view of all the moving pieces in a factory also opens the door to just in place, reducing floor usage. All of that, again, driving operational efficiencies for a lot of businesses. Knowing where people, automatic guided vehicles, robots are in real time would also help prevent accidents by controlling their interactions and by keeping humans away from hazardous areas. Last but not least, knowing where people and assets are in real time can bring a new level of security, whether it's protecting physical assets, data, or protecting communications. Because the physical presence of an object in a specific location cannot be faked, and that can be used as a new security credential. As you can see, location data goes way beyond finding stuff or finding a way in a shopping mall.
Now, that's true. So, in order to reliably deliver accurate information, Mikhail, what other design aspects do we really need to pay attention to?
To deliver value to the end users, we need to think about all the critical aspects of their applications. High accuracy is obvious. We need to be able to match the scale of people and objects as small as they can get. On this slide, I put 30 centimeters because with a 30 centimeter accuracy, you can cover 99% of the applications. But we start to see more and more applications down to single digit centimeters accuracy in terms of requirements. Reliability is even more important. It's nice to have something accurate, but if it's not reliable, how do you plan to build analytics and automated systems? Because getting accurate data only 70% of the time is pretty much useless. You need something much more reliable. Scalability comes next. We no longer talk about connecting and locating a handful of devices. We're talking about locating thousands, if not tens of thousands of devices. Then we have the usual suspects, low power and low cost. We're talking about high volume applications, applications which are cost sensitive. We're talking most of the time of applications where the devices are battery operated, so being low power will be very important. Last but not least, real time is also very important. Because knowing where an object or a person was 5 seconds ago is not of much value if you intend to build automated systems. You need to know it now.
Absolutely. Now, Mikhail, so what is the location technology state of the union today?
Before I start, because I'm going to be harsh on a few very popular technologies, so I want to say that I love my Wi-Fi. I love it to work, to stream. I love my Bluetooth to connect my headset. Those are fantastic technologies. But when they are used for what they were intended for, data communication, if you start to take them into location applications, it's a complete different picture. Engineers have done processes trying to build location systems based on Wi-Fi and Bluetooth, but they still fall short on all our requirements. Again, nothing against them. It's just that none of them were designed to deliver real-time location services. Their accuracy is in the meters. Reliability far from the 99.9% that is required to build safe and trustable systems. You cannot have thousands of tens of thousands of those devices all reporting their position simultaneously. That's just not possible. And even on what is usually their strengths, they struggle when you bring them in a location system. BLE is the best example. BLE is unbeatable for low-power data communication applications. But the number of measures and post-processing required to get one OK location is just taking power consumption through the roof, not to talk about latency in the seconds. I also get questions about RFID, but as you can see, I put RFID in a completely different category. The reason is that I consider that RFID is not what I call a continuous location technology, in the sense that the only thing you get is the last known position, the last time a tag passed by a reader, because that's how it works. And those readers have such short range that it would be difficult and expensive to get a full coverage of a venue.
Sure, that makes sense. And Mikhail, it seems like none of those answers are what we really need. Is there some other kind of technology we should be looking at for real time location?
I guess it's time to introduce you to ultra-wideband. Ultra-wideband is a technology that was designed specifically to deliver micro-location and secure communication. We're talking about location accuracy in the centimeters. So we're at least 100 times better than Wi-Fi or Bluetooth. We're talking about a technology that is ultra reliable thanks to a high immunity to multipass and interference. We're talking about a technology where you can get updates up to 1,000 times per second. That's 50 times faster than the best GPS. We're also talking about a technology that is affordable in terms of power consumption, cost, and the processing that is required to get a location point. You see this little tiny chip at the top right? This single chip gives you the answer. No need for complex systems or complex post-processing. Last but not least, ultra-wideband is based on an international standard called the IEEE 802.15.4a and 4z. And the 4z version is adding what we call distance bounding protocol to guarantee that the signal is secure.
Okay, so Mikhail, how does ultra wideband hold up against these other technologies you talked about?
Yeah, I realize I've just made a lot of claims, so time to go into a bit more details to explain the magic behind ultra-wideband technology. And in fact, there's no magic. It's all down to physics. Physics is the reason why standard technologies like Wi-Fi or Bluetooth cannot deliver what we need. And that's the reason why ultra-wideband is so different. At the top of this slide, you see what we call RSSI, Received Signal Strength Indicator. And that's roughly the standard way of estimating a distance with Wi-Fi or Bluetooth, because in theory, the distance and the received power are connected, they are linked. But that's in theory, or that's in a lab in a perfect environment. As soon as you take those implementations in a real world environment, they just fall apart. And the reason is that they are very sensitive to multipass, to interference, to obstructions. And the outcome is that the performance is pretty poor. And that's when engineers started to scratch their head. Could we use Wi-Fi and Bluetooth in a different way? And they came up with what is called time of flight. Instead of leveraging the power that is received, let's try to measure the time it takes for the signal to go from point A to point B. The problem is that those technologies are what we call narrowband technologies. That means they're fairly narrow bandwidth, 20, 40, 80 megahertz. If you convert that in the time domain, because it's hard to visualize frequencies, that's this nice little sine wave that you see in the middle. But the problem with sine waves is that they are also sensitive to multipass and interference. Anytime the signal will bounce onto the walls, you will create an error. And that's how you end up with, it's better than RSSI, but still pretty far from what we need. Now at the bottom in this blue box is how an ultra-wideband signal looks like. Ultra-wideband, as the name stands, is an ultra-wideband signal, meaning 500 megahertz of bandwidth. Those tiny, tiny little pulses, they're only 2 nanoseconds wide. And because they're so short, they're highly immune to multipass and to interference. That's how we get to below 10 centimeters of accuracy with a very high level of reliability. So again, no magic, it's just physics.
Okay, that makes sense. So, Mikhail, can we dig into how exactly this ultra wideband works?
Sure. So now we have an RF signal with properties tailored for location. So let's go deeper into the time of flight concept I briefly touched upon on the previous slide, because this is the basic principle behind all ultra-wideband implementations. With time of flight, what is important is when a signal arrives to the receiver, not its power or amplitude. In the example here, if you look at the box on the top left, the yellow little box transmits a signal. This signal will take different paths, what we call a direct path, which will go through the walls, the shortest path, and the signal will also bounce against the walls before it reaches this red dot. On the top right graph, the direct path through the wall is highly attenuated. This is this tiny signal on the left side. But as long as we can receive this signal, it doesn't matter. We can stop our clock watch and get a timestamp of the shortest time, the shortest distance traveled by the RF signal. Now let's take two devices on the bottom left. Radio 1 sends a signal and starts its clock watch. Radio 2 receives the signals and immediately sends it back to Radio 1. Radio 1 received the signal and stopped its clock watch. The time it took the signal to do a round trip is multiplied by the speed of light divided by 2, and now R1 knows its distance related to radio 2. This implementation is called two-way ranging. The equation you see on the right is, of course, a simplified equation. In reality, we take into account the actual time it takes radio 2 to process the received signal and send it back, but I wanted to keep it simple for this first introduction. Now that I've introduced the basic principles of two-way ranging. So as I explained, two-way ranging will give you the distance between two devices. Now, if you look at it in 3D, I think we all live in a 3D world, what you know is that the other device is on a sphere with a radius equal to this distance measured. This is what we call the point-to-point or the bubble. That's our top left graph. But you can implement ultra-wideband and time-of-flight in different ways depending on what you need to achieve for your application. On the top right, the infrastructure-based topology, which allows you to get an actual absolute XYZ position of devices. This is a typical asset tracking implementation. On the bottom left, a mesh implementation for applications that cannot rely on an infrastructure, and where the relative position of the devices is all what you need for your application. Last, on the bottom right, we have an angle of arrival implementation, which enables relative positioning with only two devices, or XYZ positioning with only one piece of infrastructure.
Okay, that makes sense. So if we're basing our location based on the time of flight of the radio signal, how is this all put together and what kind of components are we really looking at here?
Okay, so to address your question, let's go a little bit deeper into the infrastructure-based implementations. We have two options here that I'm going to detail in the next two slides. So the first one on this slide is based on the two-way ranging scheme we discussed earlier. So two-way ranging, you get a distance. In this implementation, fixed anchors are installed in a building. You measure the position of those anchors, you record them, store them, and you plot the position of those anchors on the map of the building. Then, the mobile device will do two-way ranging with all the accessible anchors around them. For each two-way ranging, they will get a distance to the given anchor and know that they are located on a circle or sphere of a radius equal to the distance. With the distance to three anchors, they will get three circles and can now compute their relative position to the anchors in 2D, as there is only one intersection to the three circles. The same applies with four anchors if you need to get a 3D location. And as the anchors have an absolute position, remember, we install them, measure their position, and we have all of that in a nice map. We now know where the mobile devices are on the map. So we get the absolute position of the mobile devices. The beauty of this scheme is that the only thing required is to know the position of the anchors, making it easy to deploy. The fact that the device and the infrastructure use two-way communication, we're using two-way ranging, also enables the sharing of data back and forth, collecting sensor data or pushing back control, like to raise an alarm on the mobile device. But there's nothing such a free lunch, and this scheme also comes with some drawbacks. To compute a single position, the mobile device has to do a lot of back and forth communication with multiple anchors, and that is increasing the power consumption. More communication also means that the number of devices in a given space will be limited, in the hundreds. It's a bit like if in a room you have one person talking a lot. It's a bit hard for the others to say anything. Same concept here. Let's move to the next potential implementation. If you're not really happy with what I just described, you need something much lower power, you need years of battery life, and you need a super high density of devices like thousands or tens of thousands of devices. TDOA, time difference of arrival, is what you need. In TDOA, the mobile devices are only blinking, one short transmission. They do it only once, and then the infrastructure does the rest of the job. This is made possible because the infrastructure is time synchronized, and the position of the anchors is also known. Every time an anchor receives a blink from a mobile device, it will timestamp this blink and send this timestamp back to a central location engine. With the different timestamps, what we call time of arrivals, of the same blink reported by different anchors, the central location engine can compute the time difference of arrival at the different anchors, and the result of that will be the position of the device by using multilateration algorithms, the intersection of 3D hyperboles. But again, there's nothing such a free lunch. TDOA has a lot of benefits, but it's also more complex in terms of deployment, as you need to keep all the anchors time synchronized. The other drawback is that in this implementation, there is no downlink communication channel, so no way to send the location information back to the tag. The tag is blind of its own location, and you cannot send back any control signals either. But of course, there's always solutions. It is possible then to build hybrid models between the previous implementation and these TDOA implementations, where the devices only blink most of the time, but will just listen from time to time to check if the infrastructure has any data for them. As you can guess, that will come with some trade-offs in terms of power consumption and density, but that's another level of flexibility to suit your application. I want to cover one last topology, the one that is called phase difference of arrival, also known as angle of arrival. In this scheme, one of the devices is equipped with two antennas separated by half of wavelengths, around 2 centimeters in the case of ultra-wideband. When this device receives a signal from a tag mobile device, in addition to getting a timestamp used to compute the distance, it will also be able to measure the phase of the received signal at each antenna. By subtracting the two phases, you get one for each antenna, you can then compute the angle at which the incoming signal arrived. Your device now knows the distance, using the two-way ranging, and the direction where the other party is located. With two antennas, you will get a 2D location, as you have an angular information only on one plane. Add a third antenna to form two orthogonal pairs, and you now get 3D location, as you have angular information on two perpendicular planes in addition to your distance. This implementation is very important to implement peer-to-peer location applications or to reduce the amount of infrastructure you need to deploy. Remember my previous topologies? You needed 3 to 4 anchors minimum to get one location. In this case, only one. Sorry, last paying lunch of the day. With this topology, the drawback is that the accuracy is no longer constant. With the other topology, whatever the distance between the mobile device and the anchor, the accuracy is always the same. With this implementation, angle of arrival, the accuracy is no longer constant, as we now have a range error, like in the previous one, pretty small and constant, but we also have an angular error.
Okay, I think all of those topologies make sense. Now, Mikhail, I would also imagine that we would need to keep our operating ranges in mind for this kind of technology. What kind of typical operating ranges are you seeing here?
You're correct. This is one of the frequent and very important questions I get on ultra wideband. What is the range? This is very important because people need to understand the number of anchors they will need to deploy in their application. And unfortunately, there's no straight answer. I could give you a nice marketing number, which is true, like 280 meters. We've seen that many times. We can do that, no problem. But the reality is that the answer is it depends. It depends because ultra-wideband can operate between 3.5 and 8 gigahertz. And like any RF engineers know, the higher the frequency, the shorter the range. It also depends because we support data rates between 110 kilobit per second up to 27 megabit per second. And the higher the data rate, the shorter the range. Last, it will also depend on the antennas you can use for your applications. If you have a fairly big product, you can put a nice big antenna with a nice gain. But what if you have a small wearable, like a smartwatch, where space comes at a premium? You will need to go for very tiny antennas. And again, like any RF engineer knows, the smaller the antenna, it's usually the lower the gain, and so the shorter your range. But even if you take the worst case scenario, you will still get 25 meters of range, knowing again that the accuracy of the distance measured is constant over this range. This means that with 4 anchors, you can still cover an area of roughly 620 square meters. That's 7,000 square feet. And you will have a constant location accuracy on the entire area. BLE in the same context would require at least 5 times that number of anchors to get to, 2-meter accuracy? Best case. And all those numbers I gave you, that's what our chipset gives you out of the box. We assume no external PAs nor LNAs. If your application requires longer range, that's an option you can investigate, and Corvo has all the right products for that. We have customers who add LNAs, PAs, specific antennas, and that can cover a soccer field with only 3 or 4 anchors.
Wow, that's cool. Now, Mikhail, are there frequency bands for ultra wideband the same across the world, or are they different for different parts of the world?
As you can see on this chart, ultra-wideband is regulated, and you have different frequency bands depending on the region you're in. But, and to go straight to the point, channel 9, 8 gigahertz, is the channel which will give you a worldwide operation. So that's perfect if you want to market a product that has to be sold in every market. But you also have channel 5, which is 6.5 gigahertz, which cover the globe, at one exception, Japan, while giving you a bit of extra range. So as you can see, you have different options depending on where you want to market your products.
Okay, cool. Now, Mikhail, I'm excited about this ultra wideband. Where have you guys seen it used in the field?
Almost everywhere. I've been on a Triben for 6 years, and that's what really I love in my business development job. It's the number of applications is endless. And in the past 6 years, it's been already deployed in more than 40 different verticals. As you can see on this slide, applications range from industrial to automotive to consumer electronics. Our technology is on the back of chickens, ferrets, racing cars, basketball players, shopping carts, and the list goes on. The number of applications that are in the need for location data is endless.
Okay, so Mikhail, real time, accurate location is more important than ever before with COVID-19 social distancing requirements. Can ultra wideband help me here too?
Oh, definitely. Ultra-wideband is the perfect technology to be used for such application. As we discussed, ultra-wideband has superior accuracy, what is very important in this application, as you can set different safety distances depending on local safety standards. 1 meter in France, a meter 50 in Germany, 2 meters in UK, that would be just impossible with other technologies to get that level of granularity. The superior precision and robustness to indoor environment is also very important to guarantee the reliability of the data and avoid false detections, or worse, miss a detection of an event. And like BLE tags, ultra-wideband tags are small enough to be worn by people and low power enough to be battery operated, so perfect fit. Such solutions have been successfully deployed all around the world in the past few months, from factories, warehouses, but down to the NFL and NBAs, which are using those tags for their summer camps.
Wow, I didn't know that. That's cool. So, Mikhail, I would imagine that ultra wideband could be really helpful in a manufacturing scenario as well. It seems like Industry 4.0 is a really big topic these days, and ultra wideband would fit in quite nicely there.
Manufacturing Industry 4.0 has been one of the early adopters of ultra-wideband technology. It can be a bit surprising because those segments are not really known for embracing cutting-edge technology, but ultra-wideband is the cornerstone for what is called the digital twin, the capability to get full visibility in real time of what is going on the shop floor. Employees, assets, tools, and floor equipment are all tagged with ultra-wideband radios. These tags help identify and eradicate workflow bottlenecks, helping the workflow become more efficient and driving operational efficiencies. The ultra-wideband tags are on the tools, forklifts, and that will help managers track their utilization, provide valuable utilization analytics, and that can help optimize the work operation but also the maintenance. Such systems have already been deployed in many large factories like car factories all around the globe, and they have proven to deliver a very short payback period, under 18 months.
I'd also imagine that this would be important in industrial areas as well, right, Mikhail?
Yes, another area where ultra-wideband has already delivered value to businesses is on improving worker safety at industrial sites. Enabling businesses to protect workers more effectively helps them achieve a competitive advantage by reducing many safety management related costs. Ultra-wideband tags will help establish virtual safety zones, set up access control where only authorized employees can gain access, mitigate forklift collisions with people and other equipment, and safely deactivate tools and work equipment if an employee is in a non-safe zone. If there is an emergency situation, ultra-wideband is also very important. If all employees have to evacuate the factory, the ultra-wideband tags on the employees will help notify floor managers that all team members have exited the building. Or if some employees are still inside the building, instead of having to search for them, you will get their exact location in real time.
Wow. Okay, cool. Are there any other neat uses of this technology that you can share?
Oh, yes, as mentioned earlier, that's the fun part of working with ultra-wideband. There are so many use cases. Another key value proposition of ultra-wideband is the capability to build new user interfaces between humans and objects. And here, let's start with robotics before we jump into our homes. On the left, you see an autonomous lawn mower using ultra-wideband to navigate a garden. The garden is equipped with a few ultra-wideband anchors used as reference points and guiding the ultra-wideband equipped lawn mower. Here, the benefit versus existing technology is that you no longer need to dig around your garden to bury a wire that would create a fence for your lawn mower. That's a task that was taking at least a full day and doing quite a bit of damage if you had to do it afterward. Here, ultra-wideband is taking care of all the navigation. In the middle image, the robotic scooter has ultra-wideband technology implemented that enables them to follow you, or to be more accurate, to follow the remote control that you have at your belt. And that's pretty convenient because those devices are pretty heavy. We're talking about 15 kilos, 30 pounds. And there are some areas like San Francisco where you're not allowed to ride them wherever you want. So what do you do with them? In this case, the answer is just press the follow me button and your robot will just follow you. That's what we call a virtual leash. Likewise, on the right, this is a suitcase that has ultra-wideband inside that can follow you wherever you go. No longer you will have to pull heavy luggage around the airport, the train station, or through other lobbies and hallways. And the list goes on. I've seen golf carts that follow you, baby strollers. That's pretty cool. And all of that is made possible because of ultra-wideband.
That is really cool.
Yes, that's really cool. Back to the user interface I mentioned earlier. If you think about it, the best user interface you can design is an interface where the user does not even notice it is interfacing with a device. This is exactly what Bill Gates described in his book, The Road Ahead, back in 1995, a house that would anticipate your needs. And this is exactly what is being shown on this example of access control. Current alarm systems require user interaction to activate or deactivate them. That's the classic, those keypads or those NFC keyring that you tap on a base station when you get home. The reality, and I'm the first one to do that, is I woke home, I just forget about it, and after a few minutes, I get the alarm blast my ears. That's not very nice. And the other way around, I just drive to the city, and after 15 minutes on the road, I'm like, oh, did I turn on the alarm? I can't remember. Not very convenient. With ultra-wideband, the user experience is completely different. It's seamless. You do not need to do anything to activate, deactivate your alarm or lock or unlock your doors. It's all made automatically. And the way it works is, you see the picture on the right, this lady and her daughter, they have this little access tag which has ultra-wideband built in. And as they approach the door, there's a sensor on the door with ultra-wideband that will be able to measure the distance and the angle. Remember my angle of arrival early on? And so your house knows exactly if you're walking towards the door to get in and will take care of, again, deactivating or opening the door. And the same works the other way around. If you leave the house will automatically lock and turn on the alarm for you. But I kept the best for the last one. That's one of my favorite applications. Have you ever dreamed of controlling objects by simply pointing at them?
Yes.
Yeah, because I don't know what's your experience, but I don't really enjoy navigating those complex user interfaces on my phone, or I don't know if you ever tried some of those all-in-one remote controls, which at the end are so complex to operate. But pointing and controlling, that's a dream. That was a dream. This is now possible with ultra-wideband enabled remote controls. Thanks to centimeter accuracy location combined with sensors like gyroscopes and accelerometers, magnetometers, this contextual remote control system knows the exact locations of the objects in your home and which one you're pointing at. Pointing at your lights, the user interface switches to light control. That's what you see on the top right. Pointing at your speakers, the user interface will propose to change the volume or switch to a new song. That's really cool. Love that one.
So, Mikhail, I remember that automotive design was on your list of applications. What kind of design implementation does that look like?
Yeah, definitely. Automotive has also been an early adopter of ultra-wideband, leveraging another key value proposition of ultra-wideband, the capability to build secure communication systems. Passive keyless entry systems, that's when you walk by your car and your car automatically opens. This is so convenient, and that starts to be widely deployed in the car industry. Most of the cars nowadays have such systems. But standard keyless entry systems suffer from a security weakness that we call relay attack. The concept and implementation of relay attack are fairly simple. An attacker will follow you after you park your car, just walk away, go to the mall. Somebody will just follow you. The attacker will carry a device, and this device can pick the signal from your key fob. Because what you may not know is that your key fob is pinging from time to time, transmitting. It's trying to reach out to your car. And so the attacker, with its device, will pick the signal and then amplify the signal. So even if your car is hundreds of meters away, you amplify the signal strong enough so that the car can receive the signal. And the car will think that the key is nearby, and so, let's open the car, let's start the engine, and your car is gone. Ultra-wideband solves the relay attack concern because the car and the key will measure their relative distance using time of flight and create a secure communication bubble, only allowing the car to be unlocked and started once the key is within a certain predefined range. As we saw earlier, the distance is time of flight multiplied by speed of light. Two attributes which cannot be spoofed. At least I don't know of anyone who can change time or speed of light yet. So that's making the solution much more secure than traditional technologies. And this is the reason why ultra-wideband has been selected by car and phone manufacturers for the next generation keyless entry systems.
Cool. Now, Mikhail, this seems like a really cool technology. When do you think it'll be completely ready for prime time?
Ultra-wideband is already on the verge of becoming the next ubiquitous RF technology in our everyday lives. Indeed, all the right pieces are in place for mass adoption. Maybe you don't know, but major phone manufacturers are already embedding ultra-wideband technology into their phones. I'm sure you recognize those pictures. This is important because phones are the main gateway into people's lives. But this is not sufficient to create network effects and develop large ecosystems. We need interoperability and regulations to guarantee that all the ultra-wideband devices can talk one to the other. And this is exactly the charter of Ultra-Wideband Alliance, Car Connectivity Consortium, and the FIRA Alliance. Create protocol to ensure that your car can talk to your phone to your door lock, your phone to the location infrastructure to allow you to navigate, etc., etc. And all those pieces are already in place.
All right. So, Mikhail, how do you see ultra wideband being used specifically in a smartphone?
As we discussed, you'll be able to access your car without a key fob, just using your phone or could be your smartwatch, by the way, and you won't even have to pull anything from your pocket. It will be just seamless. You will also be able to pay in a very secure way without having to take your phone out of your pocket. It will be fully automated. You will easily find items that you misplace. You remember the remote control that gets lost in your living room? With ultra wideband, just take your phone, it will pinpoint you to the exact location. Oh, again, it fell behind the couch. You will also be able to locate your family and friends in crowded areas and have seamless home automation, as we've seen. That's just the start. And exactly like nobody could anticipate the breadth of new applications that GPS, Wi Fi, or Bluetooth would enable, or new businesses. Remember my example with Amazon? I believe that engineers, product marketers, and consumers will unleash their imagination and leverage ultra-wideband capabilities into a million and one solutions.
Very cool. Now, Mikhail, what does Corvo offer specifically in the world of ultra wideband?
We offer quite a lot of things. Obviously, our portfolio includes the chipset, that's a cornerstone, and both industrial and automotive grade. So those are the two little things you see at the top of this slide. But we also decided to go beyond chipsets and offer turnkey modules to reduce the burden on our customers' R&D teams and reduce the cost of adding ultra-wideband to their products. Those modules have been designed by our own R&D team and leverage years of expertise in ultra-wideband hardware design. Most of them are also certified, removing another pain point and cost for our customers. Those modules are being used in different ways by customers. Some will only use them for their proof of concepts, what allow them to go from an idea to a demonstration in a matter of a few weeks. Other customers will leverage the economies of scale we provide them through those modules and integrate them into their end products, because at the end it's not much more expensive than using a chipset. We also clearly understand the efforts and challenges related to software design. This is why we offer a portfolio of different software solutions. We cover the different topologies I described earlier, two-way ranging, TDOA, AOA, and our solutions are available either as turnkey solutions or building blocks for the customers who want to add their own secret sauce. And all of that, all those solutions, again, help reduce our customers' development time and efforts.
So, Mikhail, specifically for the DW1000 and the DW3000, what kind of specs are we really looking at here?
So DW1000 is our first generation product, which has been in production for several years and that has already demonstrated its capabilities and quality across many different markets and applications. This is the chip being used in all the applications I presented earlier. We're now just starting to sample our second generation chip, the DW3000. This new generation adds the support of the latest version of the IEEE standard, the 4Z. The 1000 was only 4A. We have also added channel 9 for customers who need to ship their products worldwide. We have also increased the data rate from 6.8 up to 27 megabit per second. This is important if you want to transfer more data, but for most customers, the benefit is that higher data rate translates into even shorter packets in terms of transmission time, further reducing the power consumption as the radio can get back to sleep even quicker. We also worked on reducing the cost of ultra-wideband solutions. While implementing 2D angle of arrival with the DW1000 required to use one chipset per antenna, we've managed to build this same function into a single chipset in the 3000, drastically reducing the cost of the solution. For customers who need 3 or more antennas, you remember my 3D angle of arrival topology, Corvo also offers switches suitable for ultra-wideband operations. Back to solution cost, we reduced the number of external components from 30 with the DW1000 down to 10 on the DW3000. Beyond cost, this is also very important for customers for whom real estate is at a premium, like in wearables. On that front, we also now offer CSP packages with the DW3000 as small as 3.1 by 3.4 millimeters. Last but not least, our R&D team has spent also a lot of time and effort working on even lower power solutions with a brand new RF architecture able to deliver the same performance as the DW1000 at a quarter of the power of the previous generation. A very important factor for all battery-operated devices. Those two chips, DW1000 and DW3000, are what we call transceivers, meaning there is no onboard brain, no onboard microcontroller to run your software stack. That's an intentional decision because the benefit of this approach is that you have a complete freedom. Our customers have a complete freedom for selecting the microcontrollers or system of chips that suit their exact needs for their project. A microcontroller on which their design team may have built an in-depth expertise. And also it allows the design teams to leverage any legacy software they have built over the years.
Okay, cool. So what does the availability look like for these ICs?
The products we see now on these new slides, those are what we call our modules. And what you see here are all the modules based on our DW1000 family, and all of them are in full production. The first module, DWM1000, it's an RF-only module. There is no microcontroller on board. This is perfect, again, for customers who have legacy software running on a legacy platform, so they just take this RF subsystem. Our second module, the DWM1001, is a Swiss Army knife solution with a comprehensive feature set, as it includes a BLE system-on-chip from Nordic Semiconductors with Cortex-M4, 512K flash, and an accelerometer to be able to detect motion. BLE is very convenient to connect the tags to a tablet or phones for configuration purposes. And it can also be used as a coarse location solution to wake up ultra-wideband only when required. The accelerometer can trigger the location of the devices only when the device is moving, or you can build also adaptive update rates based on the activity of the device. As an example, if embedded in a wearable, customers could define an update rate, let's say, of 1 update per minute if the person is not moving. Like you're at your desk, there's no point reporting your position every second for that. But if you start walking, 1 per second might be the most appropriate update rate. Or if you start to run for some reason, 10 times per second might be what you need. This capability is very important to further improve the battery life of the tags, and all of that is configurable by software, so very flexible. Our third module at the bottom, the DWM1004, is designed to address cost-sensitive tag application. We selected a tiny and very low-power microcontroller, sufficient for basic location schemes like TDOA tags, while keeping the cost down. We kept the accelerometer, like on the DWM1001, because it really brings a lot of value on the energy consumption front. Like we did for the DW1000 family, we're also going to offer in the coming quarters different flavors of modules based on our new DW3000 chipset. The first one that you see on this page is called the DWM3000, and it will be available by early Q4, and it will be the same spirit as the DWM1000. It's an RF-only module, removing the complexity for customers to design the RF part of the product while maintaining their software legacy if they already have built software on different microcontrollers.
Okay, cool. Now, Mikhail, if I'm ready to get started using ultra wideband, do you guys have any eval kits or dev boards to throw my way?
Oh, yes, definitely, we do. We believe it is very important to offer the tools that will allow our customers to first evaluate the technology without having to do any development. That would be clearly a barrier to adoption. So we currently offer two options to suit the different needs of customers. On the left, the MDEK 1001 is based on our ultra-wideband BLE module that I just described earlier, and that's a turnkey real-time location system. All what a customer needs to perform an evaluation within minutes, from the hardware to the embedded software to the gateway firmware, PC and Android applications, all of that is available out of the box. While this solution is perfect for evaluation, you can use the same hardware and software to design an actual end product because we offer APIs that give some degree of freedom to our customers so they can put their own secret sauce, their own customization. On the other end, on the right, we also offer shields compatible with the Arduino format, a format supported by most microcontroller and SoC vendors. The goal here is to let customers reuse their favorite platforms and reuse any legacy software they may have. So it's not as turnkey as the MDEK, but you have much more flexibility for whatever you want to do. For the shields, we currently have two shields, one for the DW1000 family, so that's DWS1000, and one for the DW3000 family, so that's DWS3000.
All right, Mikhail, where should I go for more information?
Oh, we have a lot of different online resources about ultra-wideband technology, products, application notes, design examples. We're very open and we share a lot. Just follow the links on this slide. I also encourage our audience to join our online tech community. We already have more than 3,000 members, engineers, and that's a very good way to feel the innovation already happening and also to learn from the experience of your peers. Last, if you feel that you do not really have the proper in-house skills to develop a product or application based on ultra-wideband, we also have a network of partners with tremendous knowledge on ultra-wideband, and they will be more than happy to assist you in your project.
Excellent. Well, Mikhail, I think that's all I have time for today. Thank you so much for joining me.
Thank you very much. That was really great spending time with you, Amelia, today.
And before we go, you didn't forget to click that link, did you? There you can find even more information about Qorvo's UWB technology. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.